We'll have three speakers. We will have Kailyn Pritchard, Owen Scholes, and Kika McFarlane. Our first speaker today is, my mind went elsewhere for just a moment, is Kailyn Pritchard. Kailyn's going to talk to us about the birth of the tangent function. Let's welcome Kailyn.
Once upon a time, a long time ago, in a land far, far away, there lived a man named Hipparchus. Hipparchus was fascinated by the night sky and the bright stars that shone down from the heavens upon the earth. More than anything, Hipparchus wanted to be able to predict eclipses. But as he tried to do this, using every astronomical tool available to him, he encountered a problem. He needed to be able to relate the side lengths and the angles in his triangular diagrams. Of course, they say that necessity is the mother of invention, and so trigonometry was born. Since the days of Hipparchus, trigonometry has evolved significantly to become what it is today. My name is Kailyn Pritchard, and my Keystone talk today will speak to one moment in that evolutionary process. The moment in the 15th and 16th centuries when the tangent function became a part of European trigonometry. Before we dive in too far, I want us to note that two of our favorite tools for accessing trigonometry today did not exist in the 1400s when my research takes place. They didn't have SOHCAHTOA, and they didn't have scientific calculators. As it turns out, scientific calculators didn't show up on the scene until the 1970s, which was less than 50 years ago. Before then, if you wanted to know the sine, cosine, or tangent of a particular angle, you had to look them up in a book of tangent tables, which appeared like this book on the right-hand side of my slide. Mathematicians would compute and publish these tables, and then anyone who wanted to could use them. Navigators, architects, astronomers, scientists, and mathematicians all used these tables in order to complete their daily work. At this moment in time, I want to bring your attention to one particular set of tables, which were published by a man named Georg Rheticus in a book called the Opus Palatina. These are a very important set of tables, and we're going to come back to them, so I want you to remember them. Okay, so now that we've established the importance and the role of trigonometric tables, let's move on and talk about what exactly it is that I did for my Keystone. So the objective of my Keystone was to determine how exactly 4 of the very earliest tangent tables to appear in Europe were computed. This is only possible because the tables I was looking at contained significant errors. So my method works by determining what they did by seeing where they created these really significant error patterns. Okay. So, just as a quick note, for those of you who may not have thought about trigonometry in a little while, this is a geometric depiction of a sine, a cosine, and a tangent on a circle of radius r. Okay, this is not a circle of radius 1, this is not our typical unit circle. This is because the unit circle also didn't exist in the 1400s, because they didn't have this thing called decimal fractional notation. And what that means is they didn't have a decimal point, and they couldn't put any numbers after it. So if all your sines and cosines are between 0 and 1, you have a serious problem in writing them down. Okay? So if they wanted more precise sine, cosine, and tangent values, they had to use bigger and bigger and bigger circles. The largest circles that I looked at had a radius of 10 billion. Okay, so flashback to geometry. In this diagram, we have 2 similar triangles, this one and this bigger one up here. And by similar triangles, we know that the ratio of the heights of these triangles to their bases will be equal. So this means that tangent divided by r is equal to sine divided by cosine. Just this, right here. So this is the formula that I used. And first I sought to determine the radius, and then I sought to determine the exact sine and cosine values that they used. Because like I said, they were really large numbers. Okay, so how did I do that? Well, it looks a little something like this. For each radius that I examined, I computed the sines and the cosines to however many decimal places Excel would let me. And then I picked the 5 most precise whole number sines, and the 5 most precise whole number cosines, and divided each sine by each possible cosine in order to generate 25 possible tangent values. Then I took those tangent values, in this case for the tangent of 87 degrees, and compared them to the tangent values which this mathematician published in his work. So you can see here, for the radius of 60,000, I've highlighted this number, this 1,908,217. And you can see that that correlates with the 0 over here on the right. So these are the differences between these values and the value that this mathematician published in his table. So if you have a difference of 0, that means you got an exact match. That's a really good thing. So this is basically how my method works. So you can see with radius 60,000, we're getting that exact match. That's a really good thing. Radius of 100,000, best we can do is 77 off. That doesn't tell us a whole lot. Not super helpful. Okay. So let's talk about Regiomontanus. Regiomontanus created the first set of tables that I looked at when doing this research. They're not the oldest tangent tables in Europe, but they're the first ones that I looked at, and they're the simplest. Regiomontanus was a mathematician and astronomer who lived from 1436 to 1476. He is undoubtedly the most well-recognized European astronomer of the 15th century. If you haven't heard of him, you may have heard of a man named Nicholas Copernicus. Copernicus was inspired by Regiomontanus' work and actually used his tables. We have evidence of this. Regiomontanus spent the majority of his career at the University of Vienna, where he studied under his mentor, Georg Rheticus. The table containing the function, which we now know as the tangent function, was published under the name Tabula Fecunda, which means fruitful table. And it was published in his Tabulae Directionum, which was one of his most popular books and undoubtedly his most popular set of tables. Okay, so what happens when we look at these tables? This is looking at basically how close I was able to replicate his values. And we can see that the least mean error, which is what we're looking for, occurs with a radius of 60,000. So just to give you an idea of the magnitudes here, 60,000, this error, this mean error, is less than 1, it's 0.9. The next closest one for 100,000 is 17 times larger. So this is much, much smaller, which gives us pretty conclusive evidence that he was using a radius of 60,000. This is further confirmed when we look at the number of his errors that I was able to exactly replicate. So of the 10 entries that I looked at, I was able to exactly match, so get those really nice, pretty yellow zeros, for 8 out of 10 entries. And I wasn't able to get nearly as close with any of the other values. Okay, so once I'm able to get those exact error replications, right, just like up here, when I was able to see this pretty zero and know that I had that entry exactly right, that allows me to know that in order to get that value, Regiomontanus must have divided 59,918 by 3,140. So I know exactly which sines and cosines he must have used. And this allows me to make what's called a sine and cosine table reconstruction. And that looks a little something like this. Now that's a lot of numbers, but don't worry, the only ones I care about are these ones. And the only thing that I care about is that in these 4 spots, this column doesn't match this one. So the reconstructed values, the ones that I can prove Regiomontanus must have used, don't match the ones in his printed sine table with radius 60,000, which is weird. And the other thing that's weird is that if we compare these reconstructed values to the calculated values, so the one that Kailyn generated in Excel, we can see that those ones do match every time. So what this means is that the reconstructed sine and cosine tables are more accurate than the tables that Regiomontanus printed right alongside his tangent tables in the same book. So we know he had better tables and didn't print them, which is strange. Same thing happens when we reconstruct his cosines. Again, we get 3 places where the reconstructed values don't match Regiomontanus's. And in each of these 3 cases, the reconstructed values do match the calculated values, so they're more accurate. So again, this is further evidence that he had a better set of tables that he was using for his computations that he chose not to publish for whatever reason. Okay, so some of you may be wondering why it makes such a big difference that this is 1 less than that. They're pretty similar, right? But I want to demonstrate to you really quickly just how significant a shift of 1 can be when we're dealing with this sort of really sensitive mathematical computation. So let's look at 88 degrees, right? Here are 2 options for cosine are 2094 and 2093. And the sine of 88 degrees for a circle of radius 60,000 is 59,963, right? So we can take that, we can divide it by each of our possible cosines that we just talked about. We multiply by a factor of 100,000, and you can see that we get 2 numbers that are about 3 million, pardon me. But the important thing is that these 2 numbers are almost 1,400 different from each other. So since we're trying to replicate error patterns, right, if he had used this one instead of that one, it would give us a very, very different result in terms of that final tangent value. So these tiny shifts that we're seeing do make a really big difference, which is why it's important that he had gone back clearly and edited his tables and improved them before he did this computation. In total, during my project, I analyzed 4 different tangent tables and was able to conclusively reconstruct the sine and cosine tables underlying those tangent tables. By examining tables of numbers, I have been able to determine that mathematicians who lived 600 years ago were seeking to continually improve upon their own work, which is a novel mathematical conclusion. In the history of mathematics, we were not aware of this previously. The other thing that this project did was it required the invention of a novel method, right? To move back from a single tangent value to two variables. And this method did not exist in the history of mathematics prior either. It's something of my own invention. And it's been adopted by a PhD student at the University of Canterbury who is using it to study ancient Arabic tangent tables. Okay, so do you remember those tables I told you about earlier? And I was like, these are important, we're gonna come back to these, yeah? I wanna close this afternoon by telling you the story of those tables. Once upon a time, not quite so long ago, in a land not quite so far away, there lived a man named Georg Rheticus. Georg Rheticus was a brilliant mathematician whose conception of trigonometry was far before his time. The greatest of his achievements is undoubtedly the creation of the Opus Palatinum, his masterwork. This was a 1,400-page book on trigonometry, including the largest and most precise trigonometric tables the world had ever seen at the time. They contained all 6 trigonometric functions for every 1/360th of a degree. The computation of the tables alone took Rheticus, along with 5 assistants, over 12 years to compute. Though Rheticus didn't live to see the publication of his tables, his student Valentin Otho ensured that they made it into public circulation. By the time that they were published, many mathematicians were awaiting their arrival with interest. A man named Adrianus Romanus was particularly interested, and he scrutinized the tables when they were published. Less than a year after their publication, Romanus announced that they contained inexcusable errors. In some places, the 15-digit numbers were often as many as the last 9 places. The tables were unusable. Rheticus's life's work was for nothing. Now, of course, Rheticus was dead at this point, and his student Valentin Otho, who had published these tables, was far too sick to correct these errors. So, Valentin Otho helped a guy named Bartholomew Pitiscus to complete the corrections that were needed. In 1607, Pitiscus published a version of Rheticus's tables, having corrected these errors, and those tables went on to be the best, most precise trigonometric tables available in Europe for over 300 years. But the errors in the original tables went unexplained. Daunted by the sheer magnitude of these tables, historians of mathematics avoided them for 422 years. Until, once upon a time, at a bar, in a hostel, in Munich, Germany, I finally cracked them, solving the mystery for once and for all. Using the method I introduced you to earlier, I was able to conclusively determine how he computed the tables down to the exact underlying values that he must have used. And it turns out that the errors weren't Rheticus's fault. His underlying values and his computations were both nearly perfect. It's just that his method wasn't as precise as he thought. Thank you.
How did you make your reconstructions of the sines and cosines?
How did I do the reconstructions?
Yeah.
Okay, so the way that that worked, okay, so you see here, once I'm able to get that exact match, so I was able to duplicate that 1,908,217, if that's the value that he published, we know just by looking at the sine and cosine that generated that value, that this is the sine he must have used, and that's the cosine he must have used. So I went entry by entry, looking at how I was able to exactly replicate that error, and what sines and cosines must he have used in order to get there. I mean, for each of these values, I looked at 8 different possible radii, and I redid this over and over and over again, and you only got exact matches when it came to 60,000, really. I mean, you got them scattered in different things, but it's pretty simple to just look up and go, yeah, okay, there's the sine, that's the cosine, that's what he must have done, because these are too diverse for anything else to be the case. Yeah.
What kinds of things would these mathematical calculations in that time period be used for?
So during this time period, these computations were typically used for astronomy. There were all sorts of astronomical problems that they were used for, including mostly star positions, so using them to compute right ascensions and declinations of stars. Basically, it's just positioning. Actually, I go over one example in a lot of detail in my Keystone if you're interested in reading it and break it right down. Primarily for star positions, almost exclusively in astronomy, tangent functions and that sort of thing. I mean, they also kind of showed up in sundial theory, but they really didn't make it into earthly pursuits until like the 1800s. They were considered too pure to be done any work on the Earth. It was only for the heavens.
All right, let's thank Kailyn one more time.